But nevertheless, so, I have to do it now because I'm leaving. I have a train to Frankfurt, and it's a mess now. So it's why I'm doing this. So very briefly, I will start with a fuzzy introduction, and I will speak about topological Hall effect in strontium ruthenate. It's a little bit different than the topic of this very particular session. Probably I will have a little bit of time to introduce you incommensurate spin crystal in a ferroelectric lead titanate, and then I will be no more fuzzy because I will finish. So I have to blame some people on this work, and the people are over there, my students, Daniela, Sam, and Doreen. Actually, Sam did most of the work I will present here, and he is now with Professor Lukaseng at Dresden. So motivation of this work was mostly the topological Hall effect in strontium ruthenate. Strontium ruthenate, you may know that it's a ferromagnet under 150 Kelvin, and it's a perovskite, and it shows interesting effects, and one of those is exactly topological Hall effect, which is mostly signed by, oh sorry, let me back, take my tools. So it's mostly signed by these humps here in the Hall effect. So, and you get this on topological or on strontium ruthenate, which is deposited on strontium iridate, and also on strontium ruthenate, simple strontium ruthenate. So it was mainly thought to be induced by skyrmions. So you see here the skyrmions, and Professor Gissen has been given a very nice introduction of the skyrmions. And these are skyrmions into magnetic materials. So, and these skyrmions practically, they introduce that anomalous Hall effect, so topological Hall effect. Due to the chirality and so on and so forth. So this skyrmionic pocket usually exists nearby a phase transition where the magnetic momentum is much softer, and actually the main ingredient in generating those skyrmions is breaking the symmetry. So, and the breaking symmetry is usually done by spin orbit coupling, so materials which are heavy. So atoms, they have spin orbit coupling. They may induce this, and they may induce the Dzielodziński-Moria interaction, that coupling, and causing this swirling. So I'm not getting too much into detail why I'm saying it's fuzzy. So, actually, the main driving force was a paper from Taiwan No's group when they claimed that if they put barium titanate, which is a classical ferroelectric material, it has a relatively strong polarization, on strontium titanate, they get a massive topological Hall effect, and that has been practically attributed to existence of the skyrmions, magnetic skyrmions, into the strontium ruthenate. In the same time, another work showing that this topological Hall effect can be induced actually by inhomogeneities in the strontium ruthenate film. So it occurs only in a very, very particular thickness of the film. So we then decide, okay, let's go and do the same things or similar things, having a strontium ruthenate film on a lead titanate, which is even much stronger ferroelectric than barium titanate. And we knew how to do that in a very, very defined way. And let's see if we have a topological Hall effect. This is a lead titanate, so you see here the transmission electron image have a high resolution and atomic resolution, and then you have dark field, bright field. I'm not getting into details. You see exactly how the atom arrangement here. It's a very high quality strontium ruthenate, and shows very nicely this topological Hall effect. Now we thought, okay, we do have this, it does this, so we have also a beautiful machine, a great machine from AtoCube, except this is the machine which is similar with ours, but except this, we are in the hole. So we are back into the cave, nothing fancy. But the machine is good, and we can do magnetic force microscopy at low temperature, exactly the range of the temperature we have. And we had also a big advantage because we have a vector field, magnetic vector field on the machine. So we start doing and looking at that, and this is the main results. Actually, the talk can stop here showing you the results. So practically, we've measured the topological Hall effect, and then we measured the MFM, not in the same time, but into the same sample, into the similar conditions. So, and then you see here that we have a zero applied field. We have a kind of structure of the magnetic domains. I'm not speaking about the magnetic domains evolving, but at the very high field, we have another no structure. So that means we have fully magnetized our film. So, but in between, we have a very interesting structure of the magnetic domains. They are starting arranging themselves, and they arrange actually in a very specific pattern when we have two periodicities. Okay, we can analyze a little bit more this, having a Fourier transform of these images. Then we see that we have a striped domain, and then we have practically two striped domains which are combined. And then we can really do this nicely by coming and selecting different peaks in this Fourier, and we show that we have indeed a double Q structure. The question, what is this double Q structure? How the magnetic momentum arrange itself into that type of double Q structure. Luckily enough, we had a work from Tokura's group showing that in a skyrmionic crystal, there is a phase diagram in which we have indeed a very small pocket of skyrmion. So, but beside of that, we have a cycloidal type of pattern, and also this IC2 phase, which is this crystal, so spin crystal, which is exactly this one. So this resembles very, very good with this crystal. So now this phase here, this phases have been determined by neutron scattering. So practically that was in K-space detection, whereas in our case we determined that in real space. So we really mapped the domains here. So and that was probably the first mapping of the domains. So we believe that we have a kind of two structures in we have this either helicoidal or cycloidal patterning. We actually don't know. We cannot say anything about that. So the only thing we can say is that we have a double Q structure, which is called by Tokura the spin crystal. No more than that. So practically, I'm ending here my talk summarizing that we have detected in real space that very interesting domain structure, and only 1 second to show if you want, the serendipity of this of the work you can have. So in the same time we're looking into vortices in strontium in lead titanate between strontium ruthenate electrodes. So something similar but not exactly the same, looking at the ferroelectric. So I'm not going so we discovered that this is again transmission electron microscopy. We discovered that we have vortices. So the polarization into the strontium, into the lead titanate, arrange itself into the vortices. But not only that, so Dorian came to me with this transmission electron microscopy, the plant view, and show me exactly that picture. So, which resembles exactly as the domain pattern we've been seeing in strontium ruthenate. So now it's lead titanate between strontium ruthenate, and that's the pattern of the ferroelectric domain. And what you have seen, it was the pattern of the magnetic domain into the strontium ruthenate on lead titanate. Isn't odd? Yeah. So anyway, so that's the same phase probably, and we have looked into details. I'm not getting here into much details. Anyway, I want to stop here just to mention that sometimes things. Sorry? Yeah, no, I'm almost done. So it's just to show that we have the same thing into the ferroelectrics. So practically, so the physics behind ferromagnets and the ferroelectrics, despite they are completely different materials, they resemble so much. We are always, the ferroelectricians like me, always behind the people which are looking into magnetics, but it's clear that it should be like this. So ferroelectricity is a rather new, 100 years old only phenomena discovered. Thank you very much.
So we have time for a couple questions.
Thank you very much. Thank you very much for the nice presentation. I have a quick question regarding the polarization of the lead titanate.
Yep.
Was it first, as soon as you grow your capping layer of strontium ruthenate, was the lead titanate polarized with electric field?
Yeah.
And
no. You don't need the electric field to polarize it because it is an in-plane strain. It's a misfit strain which keeps the lead titanate fully polarized in one direction due to the strain you apply by growing.
But then you see the vortices in the lead titanate, right?
Oh, I mean, so if we speak the lead titanate, which has been used for strontium ruthenate, that is a bit thicker. So it was something like 20 nanometers, and that goes into the normal ferroelectric phase without any problem. So it has all the dipoles are top aligned. It's absolutely no problem. If you go into a thickness range which is about 10 unit cells, 10 to 12 unit cells, so you get that swiddling phase. Otherwise, you won't get it.
Thank you very much.